Okay, so today we're looking at the definite integral to understand area under the curve. Or we're using our knowledge of area under the curve to understand the definite integral. They kind of go hand in hand, and here is why. The definite integral. If f of x is a non-negative function, okay, so let me draw a non-negative function, more or less. And we're going to call that f of x over a closed interval from a to b. So let's make that a and this to b. Okay, then the area is the integral of f of x with respect to x from a to b. And it is also the limit of our RAM sub n as n approaches infinity. We're kind of missing the subscripts here. Okay, so we kind of looked at how we can get an area under a curve, okay, using a rectangular approximation, but that was only an approximate. Then we learned how to get the exact value using limits for the area. But this is another way in which we can find the exact area on the curve. But the way I'm expressing this right now is to find the area under a curve that's a non-negative function. So I drew f of x this way. It can also touch the x-axis. So just want to let you know, okay, something like that can work. And you can do the area under the curve here to here or here to here, whatever you desire. But if f of x is a negative function, okay, so now it's describing it as entirely negative. So let me erase this so I can draw that second part. Please make sure you get this down into your notebooks. Don't just stare at it in a video. Okay, so if it's a negative function, then let's say it looks something like this. Okay? And we're looking to find the area between a and b of this function. We can still find the area, but because it's below the x-axis, or even if it touched the x-axis, you would have to do a negation of either when you do the limit of Rm sum n or the negation of, and I think you guys can see it, the integrand of f of x with respect to x from a to b. So let me go over the notation a little bit of what you see here. So the integral sign looks like a stretched out S. That's what I heard it looks like from students, so I'm just going to go with that. And it's an integral sign. Okay. Down here is your lower limit. Up here is your upper limit. And the word upper and lower is not very clear, but I am saying it as I'm writing it, so make sure that you get that down. The expression right here is called the integrand. It's usually like f of x, such that right here would be with respect to x. That's how we read it. This is called your variable of integration. And they should, I'm running out of space, integration, be the same variable, okay, your function and what's written here. If not, you have to rewrite the function before you integrate. With that too, I suggest to put variables by your lower and upper limits of integration, what that equals. In future lessons, okay, we may change the variable here. For example, that it's a function of u and this is du, but then students end up leaving these values as x equals, and we can't have that. Everything kind of has to flow in order for you to evaluate it. So everything has to be in respect to the same variable. So typically, if this is f of x dx, then this is equal to x and that is equal to x. That is true. It may help you write the variables now that they equal x for future lessons. Just a little pointer. Okay, if you didn't get something down, please do. You can always stop the video and kind of proceed from there. Okay, so we have these examples. We're not doing any rules of integration, nothing. We're just trying to figure out what we have written and how we can evaluate it without any rules, okay? So, the first thing we're going to notice is that in number 1, our function is f of x. And if we're to graph this, it is a semicircle. So the thing with semicircles is that, well, you can find the area under the curve. Now this semicircle that I'm drawing for our function, I'm just going to call it y here. We're trying to evaluate the area, possibly, from -4 to 4. And it is possible that this is the area we're trying to evaluate. Okay? So this is a way in which we can evaluate an integral without any rules or formulas. You just need to find the area under the curve. So, since it is a semicircle, we know that the area is 1/2 pi r squared. So we need to find 1/2 pi times 4 squared. Okay, and we get 8 pi. Well, you know what? That's the answer for this integral. We just evaluated it. It's 8 pi. Because remember that this can be just area. Our function is entirely above the x-axis, so we were able to find the area and say that that evaluates the integral. So let's do the next one. So number 2, if we were to graph this, okay, then I actually have something I hope was on our homework assignment that I didn't kind of eliminate it. So we have x squared plus 3 from 0 to 2. Okay. And that's what we need to find the area. Oh, how wonderful. It wasn't from our homework. If you look at your worksheet that you had in your previous lesson, the one that says area under curve, find Rm sub n, and then using limits, find the area under the curve. Well, we actually found the area under the curve, okay, for this particular problem. We set up all these rectangles. This is 2 over n, 4 over n, 6 over n, etc. And we found the area to be 26 over 3 square units. So you know what? That is our answer for evaluating this. So it's kind of like a free response question in your AP exam, because sometimes one part, maybe part A, helps you figure out part B. So kind of see if that is the situation. Now let's take a look at number 3. So number 3, it says find the area bounded by the x-axis and the function f of x equals negative radical 36 minus x squared. So in this particular problem, this is another semicircle. Okay? Now, this semicircle is below the x-axis. This is number 3. That's what that was there for. And when you're finding the area, if you want to write the integral, you have to negate the integral. Okay, but essentially it's exactly what's being described. We're bounding it to the x-axis, and we end up, okay, that the area, okay, is 1/2 pi r, in this case 6, squared, which is 18 pi. Okay, so the answer here is 18 pi square units. This is the correct answer for number 3. But I just want to point out that if you were evaluating this would actually have a negative answer because it's below the x-axis, and we negate that to state the correct area of positive 18 pi. Okay, so it's kind of a little bit into the future lesson that we have with definite integrals, but I think it's something that you guys can understand. So I'm going to give you some practice to do. Let me know if you have any questions. Good luck.